Okay, in today's lecture, we're going to discuss the section 4.2 material on direction fields. Now, direction fields are a way to visualize the behavior of solutions to a differential equation without actually having to solve that differential equation. So we saw in our last section, and we'll see a little bit later in this chapter, that certain differential equations can be pretty difficult to solve. So if we just want to get some information about our solutions without actually having to solve an equation, we can use direction fields to do that. So let's consider defining a direction field. What exactly is our problem of interest in this section? So throughout this section, we will be considering a first-order differential equation, which would be something of the following form. Y prime, so it only involves the first derivative, could be some function of x and y. Now we know geometrically the derivative of a function, say y prime, represents the slope of the tangent line to the graph of that function, say y of x. So in order to get some information about how our solution y of x might behave, let's consider choosing a lattice of points, xy, in the xy plane. Now what I mean by a lattice of points is just a grid or collection of several points in the xy plane. And for any point xy, we can look back at our differential equation and plug that value for xy into this function f, which will tell us y prime, the slope of the tangent line to the graph of y at the point xy that we chose. So for any point, we can calculate the slope of our tangent line and sketch a line segment that has a slope of y prime passing through the point that we chose. And by doing this for many points, or several points xy, we obtain something called a direction field, which will describe the overall behavior of our solutions to the given differential equation. So this seems a little abstract when we're discussing it at first. So let's look at a specific example of sketching a direction field to help illustrate the point and make it a little more concrete. So here we're asked to draw a direction field for this differential equation, y prime is y minus 2. And then based on our direction field, let's determine the behavior of our solution, y, as x becomes infinitely large. So here, to get a direction field, we're going to start by choosing a lattice of points in the xy plane. So let's start by looking at some points within the xy plane. Maybe at first we'll just start in the first quadrant. And we can choose different points here, maybe the origin 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, and so on. We could choose the point 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, and so on. And then keep increasing the value of y, say 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, and so on. And maybe one more y value. Let's say if y was 3, we could choose the points 0, 3, 1, 3, 2, 3, 3, 3, 4, 3, and so on. So we're choosing a lattice or some grid of points in the xy plane. And for each of these points, we're going to calculate y prime, the slope of our tangent line to the graph of this function. So starting with the point 0, 0, if y is equal to 0, we see that our derivative, y prime, would be negative 2. So through the origin, we're going to draw a little line segment that has a slope of negative 2, so relatively steep and negative line segment. So if we were to move on to our next point, let's say 1, 0, well, y is still 0 for this point. So y prime, which is y minus 2, would still be negative 2, because in this example, our differential equation only depends on y. It doesn't matter what the x value is. So therefore, for every point on the x-axis where y is equal to 0, we're going to have the same slope of negative 2. So we can draw the same sort of line segment through each of those points. Now by looking at another point, let's say 0, 1, well, if y is 1, we find y prime to be negative 1. So we can draw a little line segment through the point 0, 1 with a slope of negative 1. So it's still a negative slope, and it's slightly less steep than the line that we had drawn previously with the slope of negative 2. And again, because our differential equation only depends on y and not x, for any point xy that has a y value of 1, we're going to get the same slope of negative 1. So for each of these points, I can draw a line segment that has the same slope. Now, if we keep moving upward and choosing larger y values, for instance, if y is 2, we find that y prime would be 0. So for any point xy on the line y equals 2, we have a slope for our tangent line of 0, or a horizontal tangent line. And if we were to keep moving upwards, say if y is equal to 3, then we would have a y prime value of positive 1. So now we have a line segment of slope positive 1 for any point that lies on the line y equal 3, regardless of our x value. So this sort of figure is called a direction field. And typically one thing that we would do to make our direction fields a little more informative is to turn these line segments into arrows. So in this problem in particular, we are asked about the limiting behavior of our solution y as x becomes infinitely large. So we're interested in what's happening with the value of y as x gets larger in the positive direction. So that means we're moving along the x-axis from left to right. So each of these line segments that I had, I'm going to turn into an arrow which points in the direction of increasing x. That is, from left to right along the x-axis. We're letting x become larger. So this collection of directed arrows is a direction field for this differential equation. Now, what good is this? What is this telling us about the behavior of our solution to this differential equation? Well, recall that each of these little arrows, or my line segments, lies tangent to the graph of y of x. That is, it lies tangent to my solution. So if I were to consider what happens to a solution, y of x, well, let's consider some initial condition. Let's say that I'm given an initial condition for the value of y when x is 0. So where I'm intersecting the y-axis. Now, for this particular choice of my initial condition, I know that my solution is going to move from left to right along the x-axis, since x is increasing. And as I move from left to right, this solution curve, that is the graph of y of x, has to lie tangent to these little directed arrows that I was drawing earlier. And we see that our solution starts to decrease. It's moving downward. Now, on the other hand, if I were to choose a different initial condition, let's say y of 0 somewhere between 2 and 3, then as our values of x are increasing, since we have a positive y prime value, our solution y of x would be increasing. And we could choose different initial conditions to illustrate different solution curves or different integral curves for this differential equation. And there seems to be a split occurring in the behavior of our solutions. There's a couple of solutions we've drawn here that are decreasing. They seem to be decreasing more rapidly, whereas one of our solution curves that we've drawn was increasing. And based off the inspection of our direction field, we can tell, or sort of tell, we might guess, that this split is occurring at 2. So if we were to choose an initial value of y equal to 2, well, we saw that y prime in that case would be 0. That is, there is no change, or no zero rate of change for my function y. So if I were to look at the graph of my solution passing through that point, well, it would be a constant value, a value of y from which there is no change. I would follow these little horizontal line segments and stay at 2 forever. So what we see here is the limiting behavior of our solution y will depend on my initial condition. What was y of 0? And we see that there's a split that occurs at y of 0 equals to 2. So let's see if we can answer the second part of this question, where we're asked to determine the behavior of y as x becomes large. So we see from our direction field that if the initial value of y of 0, is anything less than 2, then it appears that the limiting value of our solution, y of x, as x becomes large, is going to decrease without bound. Our solution curves keep getting larger in the negative direction, tending towards negative infinity. Whereas if we have an initial condition, y of 0 greater than 2, then our solution appears to be increasing without bound. So as x approaches infinity, it looks like our solutions are growing to become infinitely large. Now there's only one case which we haven't yet considered. That would be the case that y naught is exactly equal to 2. And we saw above from our direction field that if y is equal to 2, y prime is 0. We have a horizontal tangent line, and our solution is a constant. For every value of x, y would be equal to 2, so the limiting value of our solution would remain as that constant value 2. So this particular case of a solution that we've illustrated here with the red trajectory is what is called an equilibrium solution. That is a solution from which there is no change, or a constant solution. So in this first example, we obtained our direction field, and then the limiting behavior of our solutions could be described by this series of if-then statements. Depending on what our initial value of y is, we have a different limit for our solution. So now that we've discussed direction fields very briefly, let's define some things that are going to be useful when we're trying to sketch direction fields. So the first thing that I want to define in a little more detail is an equilibrium solution. So in this last example, we saw that if y was equal to 2, y prime is 0, which means that y would be constant. There is no change. So this is an example of an equilibrium solution. It is a solution of a differential equation for which there is no change. In other words, a constant solution, so y of x is equal to some constant c, and in order to find equilibrium solutions, well, we're looking for where there is no change. Where is the rate of change, or the derivative of y, equal to 0? And we saw, at least from our first example, that all of our solution curves in blue, so any initial condition other than 2, our solutions tended to move away from that equilibrium solution in red. They're moving outward from that solution. Now, in other examples, we'll have solutions that move towards that equilibrium. So in general, we'll say that solutions may approach or sometimes move away from an equilibrium solution over time, or as x becomes larger. So in the next couple of examples, we will consider some other direction fields and find equilibrium solutions and determine whether solutions close to those are moving towards them or away from them. So in our next example, we are asked to draw a direction field for the following differential equation. Y prime is 2y minus 3. And then based on that direction field, determine the behavior of y as x becomes large. And as we did in that first example, we say if this behavior depends on the initial value of y at x equals 0, describe that dependency. So here in the lecture notes, I've already given you the graph of your direction field. Now, in general, if we had not been given this graph, typically the first thing that we want to do to sketch a direction field is look for equilibrium solutions. And recall that an equilibrium solution is found by looking for where there is no change. That is, we're going to set our rate of change, y prime, which is 2y minus 3, equal to 0, and then solve for y. So here we find y is 3/2, or 1.5. And we can see from our direction field here, well, if y is 3/2 or 1.5, then there is a constant solution or an equilibrium solution, no change. Now, once we know where our equilibrium solution or solutions are, we can start choosing other points x, y around this equilibrium solution. And we see here, well, if we were to choose some other values for y, maybe if y were equal to 2, then we would have y prime is equal to positive 1. So for any point on the line where y equals 2, we have a tangent line that has slope positive 1. So we get these little direction arrows. And if we were to keep making y larger, say 3 or 4, y prime, which is 2y minus 3, would keep getting larger. So as we're moving upward, we're getting these little direction arrows with steeper and steeper positive slope. So here, for the sake of time, I've included this direction field in your lecture notes. And we can see, well, if we were to move downward from 3/2, say if y were 1, then y prime would be negative 1. So we start seeing little downward facing direction arrows for smaller values of y. If we keep decreasing the value of y, we're going to get larger and larger negative slopes. So from the direction field that we're given here, we can try to determine the behavior of our solutions as x become large. And again, we see there's a split in limiting behavior. It looks like for any initial value of y that starts below 3/2, our solutions very rapidly start to move towards negative infinity. They're decreasing without bound. Whereas if I choose an initial value of y greater than 3/2, we see our integral curves, the graphs of our solutions, are increasing without bound. So in order to describe this dependency on the initial value, let's again make some if-then statements. So here, I'll start by saying if the value of y when x is equal to 0 is anything greater than 3/2, then it appears that the limiting value of our solutions would be infinity. Our solutions are increasing without bound. Whereas if y naught is less than 3/2, then our solutions tend towards negative infinity. They are decreasing without bound. And then the only other case which we haven't considered is that case of an equilibrium solution. If we started at a value of exactly 3/2, then y prime is 0, and we have an equilibrium or constant solution of 3/2. And the limit of any constant is whatever that constant is, in this case 3/2. So in this example, we're kind of giving a guideline for how to sketch these direction fields. Typically, we want to start by looking for equilibrium solutions and then moving outward from those equilibrium solutions, we can sketch a few solution curves and start to determine our limiting behavior based off of this direction field. So let's look at another example similar to this, but maybe a little more complicated. Here we are asked to draw the direction field for this differential equation. Y prime is y times y minus 5. So again, I've given it in the notes here for the sake of time, but we know if we didn't have this direction field given, we would want to start by finding our equilibrium solutions, which are found by taking y prime, which in this case is y times y minus 5, and setting it equal to 0, which means that we would have two choices for y. Y would either be equal to 0 or 5. So for a direction field, if y were equal to 0 or y were equal to 5, we would have a constant solution, or a solution trajectory of just a horizontal line. And we find these equilibrium solutions at 0 and 5. Now, by choosing values of y that are above or below these equilibrium solutions, we can find the slope of our tangent line and see what's going to happen with the behavior of our solution. So if we were to move, say, upward from 5, if y were equal to 6, then y prime would be 6 times 6 minus 5, or 6. We get a pretty large positive slope right away. And we see from our expression for y prime that the larger we make y, we get very large positive slopes for our tangent line right away. So it looks like for solutions that start with an initial condition greater than 5, they're going to be diverging pretty rapidly towards positive infinity. Now, if we choose a value of y that's less than the equilibrium solution 5, let's say 4, we would have y prime is 4 times 4 minus 5, or negative 4. So we have these line segments with a slope of negative 4. And as we start to decrease the value of y, say letting y be equal to 1, for instance, we would have 1 times 1 minus 5, or again, negative 4. So we have the same sort of slope down here. And if we were to choose values of y less than our other equilibrium solution of 0, let's say negative 1, y prime would be negative 1 times negative 6, or positive 6. So we start seeing for negative values of y a positive value for y prime. So it appears that for solutions that have an initial value between 0 and 5, our solution curves will initially move downward, and they start flattening out as we're moving towards 0. The closer that I make y equal to 0, the slope of my tangent line y prime gets smaller. It's flattening out, moving towards this equilibrium solution of 0. And if I were to look at initial values of y that are less than 0, then initially our solution curves are increasing. And again, as y moves towards 0, y prime gets smaller, and it looks like our curves are closing in on 0. So let's see if we can describe this limiting behavior of our solutions based on this direction field. So we see that there's a split in limiting behavior that's occurring at 5. In particular, for any value of y when x is 0, which would be greater than 5, we see that the limiting value of our solution, y of x, seems to be infinity. It looks like our solutions are going to increase without bound. Whereas if y of 0 is anything less than 5, we're seeing our solutions appear to move towards 0. They're closing in on that smaller of my equilibrium solutions. Now, the only other case which we haven't yet described is the case that y naught is exactly equal to 5. And in the case that y of 0 is 5, we have an equilibrium or constant solution for y. Y would always be equal to 5, so its limiting value would still be 5. So here we've managed to sketch our direction field, and based on that direction field, describe what the limiting behavior of our solutions might be as x becomes large. Now, in the next couple of examples, we'll consider some differential equations which are not so easy to obtain direction fields for without making use of software. So not so easy to sketch by hand here. For example, let's suppose that we have the first order equation y prime plus 3y is equal to x plus e to the negative 2x. And we want to visualize a direction field for that equation on the window from x equals 0 to 5 and y equals negative to positive 2. So we could think about choosing several different points, x, y, in the plane, and plugging them into our expression for y prime. Now, if we solve this equation for y prime, we would have to subtract 3y from both sides, so we would have x plus e to the negative 2x minus 3y, and because of this exponential function, e to the negative 2x, it becomes difficult to evaluate the slope of our tangent line, y prime, because we don't really know, well, what is, say, the value of e to the negative 2 power if I chose x to be 1? We don't know that very well without the use of a calculator or software. So in some cases, we must rely on using software to plot these high-quality direction fields for differential equations, which we might not be able to do by hand. Now, one application or one software which is really nice for sketching these direction fields is a Java app known as dfield, which was created by a professor at Rice University. His name is John C. Polking, and this is a really nice, simple app for sketching these direction fields for more complicated differential equations. Now I can't pull it up here on the current video that I'm working with. I'm going to have to send out another video that illustrates the use of dfield since I can't do it on this iPad. But I'll send out another video illustrating how we can use dfield to get these direction fields that I've been including in the lecture notes so far, something that looks really nice without us having to do a lot of algebraic work. Now, one thing that we could look at for this differential equation or direction field that we were considering earlier would be the limiting behavior of solutions. So we want to see, well, are we moving towards or away from some equilibrium? So in order to consider an equilibrium solution or an equilibrium curve, we could let y prime, which is x plus e to the negative 2x minus 3y equal to 0, and solve for y. So here we have x plus e to the negative 2x would be equal to 3 times y. So if I solve for y, I would have 1/3 of x plus e to the negative 2x. And if we're interested in the limiting behavior of my solution as x becomes large, well, we see that y of x would be approaching a line of 1/3 x. Here, we can see that by thinking about the limiting value of this function. So this e to the negative 2x term, as x becomes large, will tend to 0, and then my solution y is approaching this x over 3 line. So we can see that in our direction field here. It looks like these solution curves are approaching the line 1/3 x. That is the line with a slope of 1/3 passing through 0, 0. So as x becomes large, y will keep increasing along that line, 1/3 x, and any solution which did not start on that line seems to be closing in on this line itself, if we follow our direction arrows. And using this Java applet that I mentioned, dfield, you can actually sketch not only these direction arrows, but also the little solution trajectories that I'm drawing in are red or blue. And I can send out a little video illustrating how that app works separate from this current video. So in our next example, we are again asked to use software to sketch a direction field for this differential equation over a rectangle where x ranges from -5 to 5 and y ranges from -5 to 5. Now again, this one's a little difficult to do by hand. I'll have to send out a separate video illustrating D fields separate from this. But if we were to consider, again, some equilibrium curves or equilibrium solutions, we might try setting y prime, which in this case, if we factor out a y, leaves us with x plus y equal to 0. And if we solve for y, we have two options. Either y could be 0, or the part in parentheses, x plus y is 0, which means that y would be -x. So if we think about those curves geometrically, well, one of them, y equals 0, is the equilibrium solution, which is a horizontal line passing through y equals 0, showing arrows for the direction of increasing x. And the other solution curve, or this other value for y that we found, was the line y equals -x. That is the line of slope -1 passing through the origin, 0, 0. So we can see in our direction field these two curves sort of divide up the plane, and depending on what our initial condition is, our solution trajectories might follow different paths. Maybe some are initially closing in on 0, whereas other ones might initially decrease before making a large increase. And we can kind of see what's happening with our solution trajectories based off these direction arrows. So again, for these few that involve software, I'll have to send out another video to illustrate how that D field app works. But for right now, let's move on to the next part of our section. So what we've been looking at in some of our early examples were differential equations where y prime, or the derivative of y, was a function of y only. So in particular, I think our first three examples were of the form y prime is like y minus 2, or 2y minus 3, or y times y minus 5. So these are examples of a special type of differential equation which is called autonomous. So here let's define it. Any differential equation of the form y prime, or dy dx, equals f of y, where our independent variable x does not appear explicitly, is called an autonomous equation. Now, autonomous equations are particularly nice to work with because we can sketch direction fields for them pretty easily, we saw. And we can determine by finding equilibrium solutions whether our solutions over the long run, as x gets larger, will approach my equilibrium solution or move away from it, as we were seeing in some of our first few examples. So here, again, an equilibrium solution of an autonomous differential equation is any solution y bar. We typically put a little bar over the variable y to denote equilibrium solutions, for which there is no change. Or again, solutions such that the derivative, which is defined as a function of y, is equal to 0. Now we saw from some of our earlier examples that solutions can either move towards or away from these equilibrium solutions. So we would say that an equilibrium is said to be stable or asymptotically stable if solutions are approaching that equilibrium. So if our solution curves are moving towards an equilibrium, it's said to be stable or asymptotically stable. And an equilibrium is called unstable if solutions that start close to that equilibrium will move away from it. So certain examples we did earlier, we saw our solution curves were moving outward from those equilibrium solutions. So what we're interested in doing for some of these problems are determining whether an equilibrium is stable or unstable. So let's look at some examples of how we could determine stability. In this next example, we are asked to consider the autonomous equation dy dx is equal to y minus 2 times y minus 6. And in part A, we are asked to find all equilibrium solutions. So to find an equilibrium solution, we're going to take our derivative, y prime, or in this case we're using the notation dy dx, which was defined as y minus 2 times y minus 6, and we set that derivative equal to 0. Now from here, it's pretty straightforward to solve for y. We find y could equal 2 or y could equal 6. So these two values of y, or these constant solutions, are what are called equilibrium solutions, and we denote them by y bar. So we're going to say y bar equals 2 or 6 are the equilibrium solutions. Now, in part B, we're going to determine the stability of these equilibrium solutions. And I kind of give some direction here about how we're going to try to do that. I start by saying, well, let's sketch the graph of y prime, which is a function of y, versus y, and then determine the stability of each of our equilibrium solutions. So let's take a look at how we're going to sketch the graph of y prime versus y. So here our graph is going to be a little different from what we're used to considering. Rather than graphing our derivative, y prime, as a function of x, well, since this is an autonomous equation, y prime doesn't depend on x. It's defined in terms of y. So here our horizontal axis will be the value of y, and our vertical axis is y prime, or our derivative. Now, for sketching the graph of a differential equation, y prime in terms of y, usually the way that I like to start is by sketching the horizontal intercepts. So those are the values of y for which y prime would be equal to 0. Now we just found those values above. The values of y, which make y prime equal to 0, are exactly the equilibrium solutions, 2 and 6. Now to determine what the graph of y prime looks like everywhere else, well, let's think about how y prime is defined. It's given by y minus 2 times y minus 6, or if we expand it, y squared minus 8y plus 12. So this is a quadratic in terms of the variable y. And we know that the graph of any quadratic is a parabola. And in this case, since we have a positive y squared coefficient, it's an upward opening parabola. So the graph of y prime, I don't know exactly what it looks like, but it is a parabola that opens upward and has to pass through the points 2 and 6, because we found those values to be equilibrium values. Now let's think about what this graph tells us about stability. So we see that for values of y between 2 and 6, that y prime is negative. It falls below the horizontal axis. So if y prime is negative, if the derivative is negative, that means that the function y is decreasing. If the derivative of a function is negative, that's when it means for a function to decrease. So along my horizontal axis, or the y-axis, that means y is decreasing. So I'm going to indicate that by drawing little right to left arrows on the y-axis. We're moving from larger values to smaller values. Now similarly, we see from our graph here that for values of y that are less than 2, or values of y that are greater than 6, the graph of y prime becomes positive. It lies above the horizontal. So if y prime is positive, that means that y is increasing. So for every value of y to the left of 2 or to the right of 6, y is increasing. So we indicate that on the y-axis by sketching these little direction arrows from left to right. And now this y-axis, let me examine just our y-axis here, gives us the following information. We had equilibrium solutions at 2 and at 6. And we had shown that for values of y that are less than 2, our solutions are increasing. For values of y that are between 2 and 6, y is decreasing. And for values of y that are greater than 6, y is increasing. So this horizontal line, our y-axis here, shows us that solutions seem to be closing in on 2. They're increasing from below or decreasing from above. We're moving in towards 2, and we're moving outward from 6. Our solutions are decreasing from 6 or increasing from 6. So the terminology that we would use is, we would say that the equilibrium y bar equals to 2 is stable. Solutions are moving towards 2, whereas y bar equals 6 is unstable. We are moving outward from that equilibrium. So this sort of diagram of the graph of y prime as a function of y can tell us about stability of these different equilibrium solutions. So this sort of diagram is what is called a phase line diagram. It tells us about where the values of y would be increasing or decreasing, and therefore tells us about stability of these equilibria. So let's look at another example of this. In this next example, we have a problem pretty similar to what we were just considering. We've got an autonomous differential equation, so that is, it depends only on y, and we are asked to find all equilibrium solutions in part A. So again, to find equilibrium solutions, we let our derivative, y prime, or dy dx, which in this case is y times 2 minus y times y minus 5, and we set it equal to 0. And from here we can see directly there are 3 equilibrium solutions. Y bar could be 0, 2, or 5. So here, 3 equilibrium solutions. And in part B, we are asked to determine their stability. So if we were to solve this differential equation, would y be moving towards 0, 2, or 5? Now, to determine stability, we could again look at a phase line diagram, similar to what we did in that last example. So let's start by graphing y prime as a function of y again. So here, my vertical axis is going to be the derivative of y, which is a function of y. And the first thing I'm going to plot on my phase line diagram are the equilibrium solutions, or my horizontal intercepts, which we found to be y equals 0, y equals 2, and y equals 5. Now, in this example, our derivative, dy dt, is a cubic. We have y times 2 minus y times y minus 5. We can leave it in this factored form. We see it's a third degree polynomial of y, so we don't know in general exactly what the graph of this function looks like. But we saw in the previous example that we really only care about whether our derivative is positive or negative. That's going to tell us about whether y is increasing or decreasing. So let's start by choosing some specific values of y to determine where our function might be increasing or decreasing. So I'll start by looking within the interval between 0 and 2. So a good test value in that interval might be 1. And if I were to plug 1 into my function, I would have a 1 times 2 minus 1 times 1 minus 5. So that is a positive times a negative, which means that the product would be negative. So I don't know exactly what my graph of y prime looks like, but I know that between 0 and 2 it must be negative, and it has to pass through those points. Now, if I were to look in the interval from 2 to 5, we could choose another test value of y, say 3, and if we were to plug 3 into our differential equation, we would have 3 times 2 minus 3 times 3 minus 5. So the product of a positive, a negative, and a negative. So that product would be positive. So we don't know exactly what the graph of our curve looks like, but it's positive between 2 and 5, and it has to pass through 2 and 5. Now, if we were to choose a value of y greater than 5, say y equals 6, and plug into our differential equation, we would have a positive times a negative times a positive, the product of which would be negative. And if we were to choose a value of y, say less than 0, negative 1, we would have a negative times a positive times a negative. So the product of those terms would be positive. So this is a rough sketch for the graph of y prime. So we can see here that on the intervals from 2 to 5, or from negative infinity to 0, y is going to be increasing because the derivative of y prime, was positive. It lied above the horizontal. Whereas on the intervals from 0 to 2, or from 5 to infinity, y is decreasing since the graph of y prime on those intervals was negative. So looking at this phase line diagram, let's review what we can say about stability. We see that solutions tend to be moving towards 0. So y equals 0 is stable. Solutions tend to be moving outwards from 2. So 2 is unstable. And solutions also tend to be moving towards 5. So 5 is stable. So again, this phase line diagram allows us to determine stability of these different equilibrium solutions. So in this example, we found that there's two different equilibria which are stable, namely 0 and 5. So the question is, well, when would we approach 0 versus when would we approach 5? And the answer is it depends on what our initial condition is. When we look at our phase line diagram, there appears to be a split in limiting behavior at 2. In particular, if I start anywhere to the left of 2 along the y-axis, it looks like we're closing in on 0. But if I were to choose an initial value of y that is greater than 2, it looks like I'm closing in on 5. So in part C, we are asking, well, if y of 0 is y naught, then we want to find the limiting value of y of t. So what's going to happen with our solution as t becomes large? And how does that limiting behavior depend on our initial condition? So we were just looking at in part B, if y naught was anything less than 2, we're going to be closing in on 0. Whereas if y naught is anything greater than 2, we're closing in on 5. So in part C, we could start by saying if y naught was anything less than 2, the limit as t approaches infinity of my solution y of t would be 0. And if y naught, my initial value of y, was anything greater than 2, then the limiting value of t as t becomes large would be 5. Now, the only other case which we have not considered is the case that y naught is exactly 2, in which case the limiting value of our solution is 2. Now, why 2? Well, 2 was an equilibrium solution. If I start at exactly 2, then we're stuck at 2 forever. 2 was an equilibrium, a value from which there is no change. So we have the following summary for the limiting value of our solutions, depending on what our starting value of y is. And then in part D, I mentioned, well, we can use software to sketch a direction field along with several solution curves. So again, making use of that program D field, we could draw a direction field and some solution curves. And we saw in part A of the problem that we have equilibrium solutions at 0, 2, and 5. And for any solution which started above 2, our solution curves tend to be closing in on 5, whereas for any solution that started below 2, our solutions tend to be moving towards 0. So we can sort of verify the work that we did in the first few parts of this problem. Now, in our last example, we will consider a different type of stability known as semi-stability for an equilibrium. So let's start by defining semi-stability. So a semi-stable equilibrium would be one which has the following property. The property that solutions which lie on one side of our equilibrium will approach that equilibrium, and solutions lying on the other side will depart from or move away from that equilibrium. So in this case, we have what is called a semi-stable equilibrium, if we're only approaching it from one side. So as an example of semi-stability, let's consider the following equation. We have the differential equation dy dt is y squared times 4 minus y squared. And in part A, we want to find all equilibrium solutions. Now, to find them, we let y prime, which is y squared times 4 minus y squared, equal to 0. So solving for y, we find, well, either y squared is 0 or 4 minus y squared is 0, which means that either y could be 0 or y could be plus or minus 2. So altogether we have 3 equilibrium solutions, 0 and positive or negative 2. Now in part B, we're asked to determine the stability of each equilibrium, and to do that we could again make use of a phase line diagram. So here we will again graph y prime as a function of y. And an easy way to graph this is by first plotting our equilibrium solutions, which we found as 0, positive 2, and negative 2. And to determine what the graph of y prime looks like, we can determine whether y prime is positive or negative on each of these subintervals. So by choosing a value of y between 0 and 2, let's say if y was 1, and we plug into our differential equation, we find dy dt would be a positive number. So between 0 and 2, y prime is positive. And for values of y greater than 2, let's say 3, we would have y prime as a positive times a negative. So here, for values of y greater than 2, y prime becomes negative. Now if we were to move to the left of 0, say between negative 2 and 0, we could take negative 1, and our derivative would be a positive value, y squared times 4 minus y squared. If y is negative 1, would give us a positive 3. And as y decreases past negative 2, say negative 3, we would have, again, a negative value for y prime. So our graph of y prime looks something like this. And from the graph of y prime, we see that on the intervals from negative 2 to 0, or from 0 to 2, our values of y are increasing. We're moving from left to right since y prime was positive. And on the intervals from negative infinity to negative 2, or from 2 to positive infinity, y is decreasing. Let me maybe use a different color here for these direction arrows. So based on this phase line diagram, we see our stability results. So let's start by looking at our equilibria from smallest to largest. Here, y bar equals negative 2, we see is unstable. So here, if we start anywhere close to negative 2, we can see that our solutions, no matter which side of negative 2 we're starting on, are moving outward from negative 2. Now for the equilibrium 0, well, to the left of 0, our values of y are increasing. They're moving towards 0, but as soon as I take a positive value of y, we're still increasing. We're moving away from 0. So in this example, we have y bar equals 0 is semi-stable. We are approaching it from one direction, but moving away from it in the other direction. And then for 2, our solutions on either side of 2 tend to be moving towards it. So we could say that y bar equals positive 2 is stable. So here we see an example of semi-stability. If our solution is only being approached from one side and we're moving away from it along the other side. That's what's called semi-stability. Now in part C, again, we're asking the question, well, depending on what the value of y naught is, that is our starting value of y, we want to find the limit of y of t as t gets large and describe how that limiting behavior would depend on y naught. So looking at our phase line diagram, if we look at the y-axis, say moving from left to right, the first split in the behavior of solutions appears to be at -2. So in particular, if y naught is anything less than -2, it appears that our solutions keep decreasing. So our limiting value would be -infinity. We can see that by looking at our phase line. If y naught was less than -2, our solutions keep decreasing without bound. Now, if I choose a value of y naught, let's say between -2 and 0, I would be moving towards 0, which is an equilibrium solution. So we could say if y naught lies between -2 and 0, including 0 itself, then as t becomes large, y of t would be closing in on 0. Now we see if we were to choose anything greater than 0, regardless of what side of 2 I lie on, for any positive value of y naught, I would be closing in on 2. So if y naught is anything greater than 0, the limiting value of y of t would be +2. And the only case which I have not yet considered is the case that y naught is exactly equal to -2. That is, if I start exactly at this equilibrium value, then I'm stuck there forever. An equilibrium is a constant solution, or a point from which there is no change. So if I start at -2, I'm stuck there forever, and my limit would be -2. And again, in part D, I mentioned that we could make use of software to sketch a direction field for this equation along with some solution curves, and we verify our results. We have equilibrium solutions at -2, at 0, and at +2. And as we mentioned in our earlier analysis, if we start anywhere below -2, our solutions are very rapidly approaching -infinity. If I start anywhere between -2 and 0, my solution curves are moving towards 0. And if I start anywhere greater than 0, my solution curves are approaching +2. So we can verify the stability results that we saw above by making use of this software. So that finishes up this section 4.2. It's a little bit of a longer section introducing some new ideas. So please, if you have questions on any of this information, email me, let me know, or stop by for those virtual office hours, or set up an appointment if you can't make it